Hi girls, we're going to have a look at a couple of things in this next little video. First of all, we're going to have a bit of a think about a geometric interpretation of what we've been working on with systems of linear equations, and we're also going to look at what a homogeneous system is. So let's start by going back to 2x2 systems, or in other words, simultaneous equations, which you'd remember from year 9 or year 10. When you were looking at those sets of simultaneous equations, it was easy to get a concept of the graphical interpretation of simultaneous equations by simply graphing the first equation, graphing the second equation, and discovering that the solution that you had come up with was the point at which the two lines crossed one another. Now we've got a gazillion ways of solving simultaneous equations now. We've used the method that you used to in year 9 or year 10. We can use a 2x2 augmented matrix and row reduction, or we can find the inverse of the matrix and its coefficients, etc. However you do that, it's still the same solution to the same geometric reality, and that is the set of points that obey this statement here, y equals 2x plus 2, and the set of points that obey this statement here, y equals x minus 1, are only both true at this one point here, minus 3, minus 4. So in this case here we have a unique solution, minus 3, minus 4. If the lines were parallel, then there would be no solution to these simultaneous equations. In other words, there's no point at which they are both true. Or an infinite number of solutions exists if the lines actually sit on top of each other, or in other words are collinear. So using that framework, let's have a look now at our 3x3 systems, and I found this image which I found really helpful to help us think about the different ways that the three equations can interact with one another. When we're looking at an equation that has an x, a y and a z variable in it, then what we're looking at is an equation for a plane. We can see from the diagram below that there are lots of different ways that three planes can interact with one another. In fact, these are only examples. There's it's probably an infinite number of ways that three planes can interact with one another, but these diagrams are useful because they give us a kind of mental picture of the different types of interaction. So if we have a look at A here, and B and C, you can see that in all of these three examples, there's no place at which the three planes converge. Here because the planes are parallel to one another, here because two of them are parallel and one is like a transversal plane, and here because pairs of the planes interact but the three don't interact at the same time. So A, B and C here would be examples of systems where there is no solution. Diagram D, on the other hand, shows us three planes which do converge, and they converge at one point. So that one point there represents a unique solution to that system of equations. So when you when you reduce a 3x3 matrix and you come up with a unique solution, then those three planes are only converging at one point. A unique solution. E is an example of where three planes can converge to form an infinite set of solutions, in fact a line. So you can see how this plane here, and this plane here are all interacting with each other, and the set of points at which they interact is this line here. So there's infinite number of points on a line, of course, so there's an infinite set of solutions. So I can hear you say, oh, when we found infinite solutions, an infinite set of solutions over the last couple of lessons, it certainly didn't look like the equation of a line. We have to remember that what we're working in here is three-dimensional space. So you're used to equations of a line in the xy plane in two-dimensional space, but we're now working in a three-dimensional space. So the equation of a line is going to look different when it's expressed in that way. So because you haven't gone into three-dimensional space, the x, y and z axes together, I won't go into that any further, but when you do finally get around to learning about representing planes in three-dimensional space, you can look back fondly to this lesson and think, that was the first time I thought about it. Okay, so hopefully that gives you some mental picture to go with your deepening understanding of 3x3 systems of equations. I want to briefly talk now about homogeneous sets of equations or homogeneous systems. So a couple of lessons ago, Caitlin asked a question. We had a 3x3 system in which every equation equaled 0, and the answer in that particular case was x equals 0, y equals 0, and z equals 0. And like a good mathematician, Caitlin wondered if we could save ourselves the trouble of reducing the matrix and just go straight to the solution that x equals 0, y equals 0, and z equals 0. That was good mathematical thinking, because basically mathematics is about doing things as simply and easily as possible. However, we then had a discussion about how it was a possibility that a system of three equations which equals 0 could have a non-zero solution. So we left it there at that point, but I'd like to go a little bit further with it today. In fact, when we have a system of this kind, it's known as a homogeneous or homogenous system, however you want to pronounce it. Here's an example down here. Whenever the three equations have 0 answers or equal 0, that's called a homogeneous or homogeneous system of linear equations. Now, we do note that, of course, a homogeneous system of linear equations always has at least one solution, and that is the solution that was referred to, x equals 0, y equals 0, and z equals 0. This is known as the trivial solution. And you can sort of see why, can't you? It actually doesn't increase our understanding all that much, this particular solution. But it is interesting to know, what we're really interested to know when we look at systems like this is whether there are non-trivial solutions. So we know that a system will have an infinite set of solutions if the number of equations present after row reduction, and if you remember back to a couple of lessons ago, that was known as the rank of the matrix. If the number of equations after row reduction is less than the number of unknown variables, then I'll have an infinite number of solutions, an infinite set of solutions. So let's look at this example. Here I've got these three equations with the 0, all equal to 0. It gives me the augmented matrix that you see there, which reduces to, I'm not going to do the arithmetic. You can have a look at it in your handout sheet. We're actually working on page 361 of the landscape handout, the one that we rejected the other day because the answers were funny. Anyway, this system here reduces to this row reduced echelon form here, and notice that I have a row of zeros at the bottom. So therefore I have three unknowns, x, y and z, in two equations. So of course I have an infinite set of solutions, and we go through that process of using the variable t, or the parameter t, to describe the relationship between x, y and z. So this leads us to a theorem for homogeneous systems of linear equations, and that is that in a homogeneous system of linear equations, a non-trivial solution exists if and only if the rank of the coefficient matrix, so that's the number of rows after you've reduced it, if the rank of the coefficient matrix is less than the number of unknowns in the matrix. So you can see that this is applicable to greater than 3 by 3 systems. If I had a 4 by 4 system which had 4 unknowns and it reduced to 3 equations, or in other words the coefficient matrix had a rank of 3, then I would also have a infinite set of solutions and a non-trivial solution. Okay, so what I'd like you to do now is have a look at exercise 8.8. This is in the handout that we rejected the other day because of the solutions, and I'm hoping that that mix-up only affected that exercise that we were doing the other day. Regardless, even if you can't check your answers, if they're not working out, it's a good exercise to practice this. So exercise 8.8, it's on page 363. Have a go. If the answers are really frustrating you, then the textbook that this handout came from is up on my desk in my office. You could go and grab the textbook and see if you can find the appropriate answers, but I'm hopeful that it won't be a problem this time around. Okay, have fun!